it's probably doing the right thing.
Yes, yes. So I was in the class for the 2:15 afternoon, so 12:30, and I wasn't here for Friday for the quiz.
Mm-hmm.
Am I still taking?
Yeah, catch me in my office at 12.
Okay.
I got one for you. All right. Questions on ODP 241 that you turned in on Friday. So 242 is posted, and that's also due tomorrow at 5 p.m., so it's a day and a half. So let's take a look at 241. So 241, you were trying to find a word inside the structure, so you're writing this find word function. And something like this, we basically talked through this on paper, right? So I have a temporary node pointer I'm calling temp, a for loop that goes through each character of the word you're looking for, and take the pointer associated with that letter and set temp equal to that. If temp is null, we're done. The word's not in the structure. Okay. If the word is potentially in the structure, temp will be non-null. It will be the address of another node, and we want to continue with the next letter, so we simply set temp equal to whatever that pointer is referring to, and we go back to the top of our loop. If we get all the way through that, temp should now be pointing to the node after the last letter, and we can just check the end of string flag. If that's 1, then the word is found, otherwise the word is not found. So the picture for that is something like this. So here's our root. And here's C, and that's pointing to another node. And here's A, and that's pointing to a third node. And here's T, and that's pointing to a fourth node. And in that node, end of string is set to 1. That tells us the cat is in the structure. So the code that we just saw basically starts off with temp equal to the root. Looks at the first letter, that's a C, so it finds this pointer, and whatever that's referring to, it sets temp equal to that. Goes to the A, finds that pointer, sets temp where that's pointing. Goes to the T, finds that pointer, sets temp to what that's pointing to. And then we're done with our word. We come out of our for loop, and at this point, temp should be this last node, so that's where we check the end of string. So if you're searching for car, C temp would come down here, A temp would come down here, R temp would be equal to null, and we'll exit right away. And if we come all the way down, but this is a 0, cat's not in there, but cats might be, and so we'd return a 0 saying the node's not in there. So 242 is the last piece of this, so we're trying to insert into the structure, so you're making a function called addWord. Returns void, it doesn't have to return any value. Takes a pointer to a struct try node, so that's the root, and it takes a string, which is the word you're adding. You can assume the word does not already exist in the structure, and it's only uppercase letters A through Z. And you're basically just writing this addWord function that will update the structure to add this word. Don't delete anything, just add this to the structure along with whatever else is in there. And so how do we do this? Well, let's add the word car. It's almost the code that you wrote for find word. So we start with temp being the root, and we look at the first letter, and that's a C. And so we see what that points to, and we set temp equal to that. And now we look at the second letter as an A, see what that pointer points to, and set temp equal to that. Here's an R. Before we go ahead and set R equal to what this is pointing to, check this pointer and see if it's null. If it's not null, just set temp equal to it and keep looping. But in this case, this is pointing to null. So we need to create a new node, change this R pointer to point to that new node, and that's set temp equal to this, and continue in your loop. So it's almost going to be the same code.
Sounds like an if statement with a while loop.
Pretty much. Right, so it's almost going to be this, except instead of just saying temp equals temp letters word I minus A, right, check this to see if it's null. If it's not, just make temp equal to it. But if it is null, create a new node, initialize it, set temp equal to that new node, but also set this up to point to that new node. Yeah?
Is there a reason why you use temp? Why not say root equals root arrow letters?
I could have used root. Well, as long as I keep updating root.
It could overwrite root.
Yeah, root's just, it's passed by value, so I can use root as a temporary, but I wanted to have a temporary variable.
Gotcha.
Yeah. All right, so check this. If it's not null, just set temp equal to it and continue. If it is null, create a new node, set this to point to that new node, and then set temp equal to that new node and continue your loop. And then if you get all the way through the loop, instead of checking the end of string bit, just set that to a 1. And when you get through the loop, temp should be pointing to the last node where you want the EOS to be 1, so just set EOS to 1 and you're done. So you got a day and a half to do this, right? Same suggestion as before. Pretend it's due tomorrow morning. Okay, try to get this done today. If you can't get it done, then we can talk about it more in class tomorrow. Okay, but don't start it tomorrow at 2 in the afternoon. All right, a couple of things to be cautious about here. One, make sure when you create a new node that you do it correctly. So you have to malloc enough space for a struct try node. It's a big structure. It's got 26 pointers and it's got an integer. So it's going to have a whole bunch of bytes in it, okay? Make sure that you're mallocing size of struct try node, not struct try node star. Otherwise it'll blow up quickly. And then initialize all of your letter pointers to be null and initialize EOS to be 0. Don't assume that those will be 0 for you. So initialize everything. So you need some kind of loop. Make a function called, you know, get me a new initialized try node or something like that. And then just set your temporary equal to that. Code this up, try it. If it works, great. If it doesn't work and it's an all or nothing, grade 1 test. If it doesn't work, here's my suggestions. 1, go through this on paper. Okay, take a try node, right, structure containing a couple of words, and go through your code and see what it's doing relative to this. And you really got to suspend your belief. You got to forget the idea that I should come down here to the R and point down here and make this equal to a 1. Right? That's what you wanted to do, but forget that. Just once you've got your code, go through your code step by step and see what it actually does to your structure. Don't put anything on here that's not reflected by something at that point in your code. Don't look ahead, don't anticipate. This is one of the hardest things about debugging. Because we know what we want this to do. It's going to go down here, and then here it's going to make a new node. Don't do that. Right? Just go line by line in your code. Pretend you've never seen this code before. Try to figure out what it does. Chances are, if you do that faithfully, you'll find something like, oh, I've got this pointing back to the root, or I've got this pointing to null, or I've got it pointing to the previous node, or something, or I didn't set this to a 1, I set this to a 1. The other option is GDB, because you can make yourself an empty node, and in your main program, right, just create an empty try node with nulls, EOS equals 0, and then just pass that to your add word and try to add a word to it. And you can run that through the debugger and go step by step. I think it's probably more direct to do it on paper, but debugger is also good. So if you pass a totally empty node where all these pointers are null, and you say something like add cat, right, what should it do? It should check this see that that's a null. It should create a new initialized try node. It should change this to point there, and then set this to temp. And then it should go to the A, it should check the A index, see that that's null, create another try node, change A to point to that, and then set temp equal to that. Go on to the T, check that pointer, that's null, create another empty try node, change the T to point to that, call this temp, kick out of your loop at that point, set this end of string to 1. And as your code is executing, you can check what it's doing. You can print star root, and you should see exactly what that's pointing to. And you should see before this a bunch of nulls and a 0. After this third entry should be a pointer. And you can say star that, and you should see this entry, and so on. So it can take a while, okay, but it's really good practice in debugging these structures, getting more comfortable with GEB.
So for 242, you're just aiming to initialize all of the letter array thingies that point to null and the EOS to be 0 from?
When you're making a new node, yeah.
Okay.
But after you've made that new node, you're going to go back into the top of your loop again, and ultimately either one of those letters in that new node is going to point somewhere, or you're going to change the EOS to be 1. But to start off with, you don't know what the letter is, so you're going to initialize all the pointers to null and the EOS to 0. All right, so other questions on that? Cool. All right, well, let's continue sorting. So I want to talk about a sort method called Quicksort, which you would hope is pretty fast. And it actually is. It's order n log n, average case. But worst case, this is a really bad sort. Worst case, this is actually order n squared. So at its worst, it's on par with a bubble sort, but a whole lot harder to code. But average case n log n, so merge sort, heap sort, most of the sorts we're going to talk about from here on out are n log n, and that's pretty good. And it turns out what makes Quicksort behave really badly is if your initial data is already sorted. If you give this a sorted array and you run Quicksort, it takes n squared.
That's ironic.
That is ironic. And so sometimes Quicksort algorithms, the first thing they do is they scramble up your input data. Because a lot of times data is partially sorted, right? For example, you have a list of 1 million names and you just added 100 new names. How do you do that? Just stick them on the end, right? And then say sort this. That would do really poorly on a Quicksort. So sometimes we randomize the data just to get rid of those possibilities or those likelihoods. All right, so Quicksort is a kind of quirky sorting algorithm. So we'll go through a few examples, and then I'm going to have you go onto the boards and do these yourselves. All right, so here's a set of 9 numbers we want to sort using Quicksort. So let me give you the algorithm. First step, we're going to pick what's called a pivot. A pivot is a number we're going to pick from the list, and our goal is to place that number in the correct position in this list, so that once the list is sorted, that number is already in the right spot. So pick a pivot to be placed in its final correct position. And usually we're just going to pick the last number in the list. That's a pretty typical choice of pivot. So typically just pick the last number. All right, step 2. Move from the left to the right, looking for a number bigger than the pivot. So we want to find the first number from the left that's bigger than the pivot, and then we're going to move from the right. I should say look instead of move, because we're not moving anything here. So look from the right to the left, looking for a number less than the pivot. And then we're going to swap the numbers that we found in steps 2 and 3. And then we're going to go back to step 2 and do this again. So we're going to loop until we're done, and then we're going to do one more step, swap pivot with where 2 and 3 met. Alright, so an example will make this much clearer. So we pick a number to pivot. We're going to start with the right, and we're going to start from the left, and we're going to try to find a number bigger than the pivot. So 3 is smaller, so we move over. 4 is smaller, so we move over. 50 is bigger than the pivot, so we stop. Okay, that's the end of step 2. Look from the left to the right for a number bigger than the pivot. So now step 3, we start from the right. Go back to step 2. So we start from the right, and we're looking for a number smaller than the pivot. So 80 is bigger. Move on to 70. 70 is bigger. Move on to 10. 10 is smaller, so we stop. So that's the end of step 3. Look from the right to the left, looking for a number smaller than the pivot. Okay, step 4, we swap the numbers that we stopped at in these 2 steps. So we're going to take the 50 and the 10, and we're going to exchange them. So now our list looks like this: 3, 4, 10, 40, 6, 50, 70, 80, 15. So this is our pivot still, and we were sitting right here from the left, and we were sitting right here from the right. So these are, temporary index pointers or something. All right, and we go back to step 2. So we look from the left for a number bigger than 15. Well, we move over here. Oops, wrong color. We move over here. 40 is bigger than 15. We stop. Okay, now we come from the right, and we look for a number smaller than 15. So we come here. If there's a number smaller than 15, we stop. Go back and swap the 2 numbers. So exchange this with this. And so now our list looks like this: 3, 4, 10, 6, 40, 50, 70, 80, 15. we've gone as far as that from the right, and we've gone as far as this from the left. Okay, so keep moving to the right, looking for a number that's bigger than 15. Well, we move to the right and we collide with where we were coming from the left. We hit a number we've already looked at. So that's where we're done. Okay, so that's loop until done. Means loop until our two arrows collide. Once we hit that collision point, we take that number and we swap it with the pivot. So this gives us our final array. So the 40 and the 15 get swapped. And I'm going to draw a big circle around this 15, the thing that was the pivot. Okay, here's what's significant about the 15. We can guarantee everything to the left of that point is smaller than 15, and everything to the right is bigger than 15. And how do we know that? Because when we were calling 15 our pivot, we were moving over and we were looking for things that were on the wrong side of 15, either from the left or from the right. And when we found two things that were on the wrong side, we swapped them. And we kept going. Well, once we hit a point where our two pointers collided, we know that everything to the left of that is smaller than 15, and everything from there to the right is bigger. And so if we swap the 15 into here, all of these are smaller, all of these are bigger. When we finally sort the whole array, wherever 15 goes, everything to the left is going to be smaller, everything to the right is going to be bigger, which tells us that 15 is now in the correct spot for the final output. Once everything's sorted, we know 15 is going to be sitting right here in this fifth position. So now, to finish sorting the original array, we've only got to do two things. We got to sort these four numbers, and we got to sort these four numbers. And we know when this is sorted, they're all going to be sitting over here on the left, and when these are sorted, they're all going to be sitting over there on the right. So how should we sort these arrays? Say it. Quicksort. Yep. Right, so that's the recursive part. So we do a little more work here than we do in some of these other recursive algorithms. We do this business of picking a pivot, moving these arrows, swapping pairs of numbers until we find where the pivot belongs. Put the pivot in there, and then we just recurse. We just call quicksort on this, and then we call quicksort on that, and we're done. And the base case for quicksort is if you're asked to quicksort something that contains only one number, you're done. Don't have to do anything, don't have to recurse, just return. It's already sorted. What? Step 6 is swap the pivot with where 2 and 3 met. So my arrows collided at 40, for example, so I swap that with the pivot. All right, let me do one more example, and then I'll show you the pathology, and then I'll let you work on this. Yes?
Will there be a case where the pivot is not the last number?
You can use anything you want for the pivot, but typically we just do the last number. And if I ask you to do this on a final exam on a Monday or a Wednesday, for example, hypothetically, I'll probably ask you to do the pivot as the last number. All right, so let's do the first step of quicksort on this. So let's still pivot with the last number. And so we start from the left, and we try to find numbers that are bigger than 6. And the first number we try, that's already bigger than 6. So we stop right there. And now we start from the right and we try to find numbers smaller than 6. Well, 18 is fine. 4 is smaller. So relative to each other, these two are in the wrong positions. So we're going to swap them. So this is going to become 4, 2, 20, 15, 7, 10, 18, 6. Draw a box around our pivot. We were up to here from the left, and we were up to here from the right. All right, so continue from the left. Look for things that are bigger than the pivot. So 2 is fine, that's smaller. Move over to 20. 20 is bigger, so stop. And now come over to the right and look for things smaller than the pivot. So 7 is bigger, that's fine. 15 is bigger, that's fine. Come over here to 20 while we've collided. Okay, our arrows collided, so we're done with our loop. And that tells us that this and the pivot should be swapped. So now we've got 4, 2, our pivot goes here, 15, 7, 10, 18, 20. And I'll draw my big circle around the 6, because now the 6 is in the correct spot. And so we're done with step 1 of Quicksort, which was we put the pivot in the correct spot. We have 2 other things to do. So we have to call Quicksort on this and put the result over here. And then we have to call Quicksort on this and put the result over here. And once those 2 Quicksorts finish, we're done. The whole thing is sorted. Pretty cool. All right, so here's what I'm going to ask you to do. Go ahead and find some friends and find a spot on the board, erase what's already up there. And I want you to make an array of 10 numbers. Oh, let me show you the pathology first, because I don't want you to do this. So suppose you decide to try to quicksort this, and it's already sorted to begin with. So here's our pivot, and we're going to start moving from the left, and we're looking for something bigger than the pivot.
Nothing's going to be bigger than the pivot.
Nothing's going to be bigger than the pivot. We're going to run out of space right here. And that's kind of an edge case right there. We don't actually swap. It tells us the pivot's already in the correct spot. So this gets our big circle. And now we have to do 2 things. We have to quicksort this and put the result here. And we have to quicksort, well, nothing, and put the result here. Well, this is easy. This is quicksorting 9 numbers. And when we run through the quicksort algorithm, or pivot of 9, right, we're going to end up having to quicksort 8 numbers, and then 7, and so on. Okay, so one of these passes is basically order n, because all we're doing is we're comparing each of these numbers to the pivot, and occasionally we're doing a transposition, so 3 steps to swap places. But most of the work is comparing each number in our original list to the pivot, so that's order n. But each time that we finish this and we get the pivot in the correct spot, we have sub-problems to solve, which involve quicksorting things that are half as big. And we keep doing this until you come down to try to quicksort something that only has 1 number, and then we say, well, we don't have to do any work, we're done. So how many times do we cut something in half before it ends up having only 1 number? Well, it's basically log n. So it's doing roughly log n recursive calls, where each call takes basically n steps. So this turns out to be n log n on average. But in this pathological case, each time that we recurse, we're working on a list that's one number smaller. And if we start off with n numbers, we're going to have to recurse n times before we get down to a list with just one number, which is n squared, right? It's n passes, n steps each. So that's your worst case, n squared. So when you come up with an array of 10 numbers, don't make them sorted. Okay, but try to pick 10, sort of randomly arranged numbers. Pick your rightmost element as a pivot, and then go through multiple passes of quicksort until you get the pivot in the correct spot. Okay, and stop at that point. I'm going to walk around and watch what people are doing. And then once you're good with that, I'll have you go ahead and pick one or two of your subarrays and use quicksort on that, or start with a new array of 10 numbers. Okay, make sense? So find a board spot, find some people to work with, and let's see how this works. Make up an array of 10 numbers.
You just review it. This is what you should do for
Oh, is it? Yeah. Are you going to do that? Probably number two.
Yeah.
There we go. Now that's.
Well, why don't you just write the arrows? What's the point of this? How you sort it? Well, you could use it this way.
Found it. Swap them.
It actually.
Alright,
Alright, so what we do now is just swap these two. Yeah, just write these two swap.
Yeah, so, yeah.
That's awesome.
So you started from the left, and how far did you get?
On a bigger one.
Okay, and then you started from the right. You shouldn't go past 20, because when you get to 20, you realize you stop at 20, and then you do 25.
So now we have to. Down 5. I mean,
this one is more pivot, right? This one
Yeah.
is more pivot.
Yeah, but that, now we would have to like
Quick
sort
sort
this,
Alright.
and then we
So
can
let's
quick
do that.
sort two.
So, this.
Yeah, now we have to like,
If it's quick sort of two sides.
yeah.
The 2 and 4 is sort of quick sort.
Alright, start with 32.
And quick sort is.
Yeah.
The bottom ones.
Actually, I think we just quick sort just the two. Because 4 is already in there.
Oh, yeah, you
Just the
quick sort.
two, so it really wouldn't do anything, so it's just return
And additionally.
Yeah.
Okay. Then we do that again, but with the new pivot.
No, I wouldn't. I don't know.
Oh,
Yeah.
So we could do this way. So this one is that, and then that. No.
Just do it all over again.
You start with this one.
What happens if they do that? Don't you do it? I don't know, try it.
Oh,
I don't think it breaks it.
Bigger. So you want things bigger.
But compared to having a line. Sure that it goes, you know.
Do the same thing.
Yeah. Handle it, I don't know what the right thing to do is there. So it's not gonna do. Did you get my email on 215, by the way?
Yeah.
Okay.
I just when I looked at it, I was like, what in the world?
Yeah.
And then I think I fixed it.
Okay.
But it didn't
We were telling you it's a less than or equal or something.
I was trying to do the square root event, but I was trying to get fancy because it said they don't need square roots. I squared both sides. But I found square both sides.
Okay. That works.
Only try to find.
Yes. 12, 49, 3, and swap.
That's 27.
So you can play around with it to see what happens, or go ahead and quick sort and then pull that for the 12. How's this look?
So yeah, rewrite all that.
Over there, 30's out, 12 is out.
One at the end.
No, I don't.
Let's fix that.
46. 46, swap those. Looks really good.
So you can try quick sorting that array of bad numbers for a second practice run if you want.
So what's the big circle? That was our previous? Civic on that drive. It's going to be in that location.
Oh, wait.
Yeah, that's perfect.
Something smaller is nothing.
So if you're looking for a number bigger than 3 and you get all the way over to the pivot, that's just an edge case. Okay, it tells you the pivot's already in the right spot. So you don't have to swap the pivot with anything. You just say, okay, this is correct. So now you quick sort that and you quick sort null.
I like this kid way easier.
Yeah, that was a wonderful circle.
That will be the same. And it's only one number, so you don't have to sort.
Yeah, and then you'll hit 50 or something, so you'll stop there. Well, then you guys, well, I guess, yeah, just check this. 21 would be less than 57. I need your base. Yeah, there you go. And then those.
No. So you started over here, you're looking for something bigger than 32, you got right there. Okay, now you start here, look for something smaller than 32, you got right here. Okay, so you swap those two. So you're not swapping with the pivot yet.
No. So we know we're done. So then, we sort the 8. Right.
And you're sitting right here, so now you keep going, to the right. Collide. Now you swap this.
So we just did the percentage wire. We compare and say what the truth or not.
Left to right, looking for a number big, right?
Yes.
In that case, what if we
So it actually collide.
So that was bigger. And then you look for something smaller right there, so you swap those. Okay, so now you keep going, you're looking for something bigger. And as bigger to bigger. And so now you start there to find bigger to smaller, but they're already collided. So you just swap the 76 with the pivot.
We quick sort this and then quick sort these three.
It doesn't actually reach that point.
Right. Yeah, from the left, you're gonna make it all the way up to here. Alright, together. How'd this work?
Actually, I think before we do another call, we would look at this again and then do the right, looking for the bigger one. Alright, yeah, I guess maybe we'll just jump in on that one.
We know 32
Yeah.
is wise, so 50 has to be the right spot. 21 is
But then you go over to 23. Then you can actually And then you look, and then you just yeah. So you circle it, and then you check again, and then 23 is looking at the right place again. You're gonna circle it again. And then you circle that.
Yeah, put it all back together.
So it goes 2,
And then you're gonna
4,
end up, yeah, you're gonna have 5. So that'll be 1, 5, 10,
4, 5, and then
1, 4, yeah.
13.
Everything else.
So in your code, you would keep going and having an IE.
Yeah.
You'd say, well, let's quick sort this. You'll end up finding the 10s in the right spot, and you'll call it quick sort on that. Go all the way down. But, yeah, that's it.
Because I thought it would do research. It's doing it.
Okay, so this is all it is. So I have it where it deletes a note if it has no children.
Yeah, and it's sorted. Awesome, very good. It works. It works. Cool. Okay. You just equal, you just call it. Yeah. Okay.
What was your name?
Quick sorting this. So this, swap that. So that's where they collide, so swap that for 13. Oh, 13. Oh, I forgot to swap it. Yeah. All right, cool. So that's Quicksort. We'll talk about heaps tomorrow. So there's a heap sort, but heaps are a thing in themselves. So so we'll play around with heaps. We'll do ODP 242 questions or PA4 questions if you have them. If you can erase the board on your way out, that would be cool. And I will see you next time.